Hello everyone and welcome back to Minic Analytics. I'm very glad to have you back once again. In this video, we are going to be conducting yet another comparative analysis. And in this case, we will be focusing on the classification algorithms. And our major goal will be selecting the best classification algorithm that best fits the objective that we will be trying to achieve. Okay, so before we get started, if you are new to this place, please consider subscribing to our YouTube channel. We are welcoming you to this wonderful community. You can also hit that notification bell so that you never miss any of our video updates. You can also like, comment, and share. Okay, so let's get started. Predictive modeling involves the selection of appropriate machine learning algorithm that guarantees accurate and reliable results. When selecting these algorithms, the effectiveness of these algorithms usually vary based on the nature of the data as well as the problem that we are trying to solve. In this case, as I had alluded earlier, we will be conducting a comparative analysis, and our aim or our objective is to evaluate the efficiency of the various machine learning algorithms, and in that way we are going to determine the most appropriate model for our case. When we are conducting this analysis, we will be ranking these machine learning models. For the ranking, we'll be examining the performance metrics such as the precision, the recall, the F1 score, the receiver operating characteristics or the ROC, as well as the precision recall curves. Because these evaluation metrics, they will offer us a comprehensive understanding of the trade-offs with each algorithm that we are going to analyze. Also, these metrics will also serve as a guide to us on the appropriate algorithm that best captures the patterns within the data. So basically, that's what we are going to be handling in this case. Okay, so without further ado, let's get started with the analysis process. So for this case, we are going to start by importing the Python libraries. So these are the libraries that we will be importing. Those include the pandas, numpy, matplotlib, as well as the seaborn. Okay. After that, I'll execute this cell. Then after that, we are going to move on to importing our dataset. So I will be using the read CSV function. Okay, then use the head method to display the first 5 rows of our data frame. So basically, this is our data frame. As you can see, we have the feature of the attributes. So these are the attributes, and within the attributes we have the entities. So inside the attributes we have the data entries. So okay. So after importing our data sets, we can then move on to another step, which involves a data summary. So we want to have a description about our data. So data summary. For the data summary, I'm going to use the info method. So when we execute this, by this method, we are getting a description about the data that we are handling, and from here we are getting information about the number of entries. So in our data frame, we have a total of 1319 entries. So basically, this is just a small data set that we will be using for illustration. We're also getting information about the total columns. So we have a total of 9 columns in our data frame. For the null count, you can see we have 1319, and it's a similar value for the other columns. So basically, in our data set or in our data frame, we do not have missing values. Also, in terms of the data types, so we have integers, floating point numbers, and for the attribute class, the objects. So in most cases, as you can see, we have categorical values in the attribute class. So basically these are text or text input. So then moving on, I will check for duplicates in our data frame. So when checking for the duplicates, I'm going to be using the duplicated method. So df.duplicated. Then inside the brackets, I'm going to use an argument keep equals false. So that means every row that is duplicated, it will be labeled as true. Then we will calculate the sum of those true values. So when we execute this, you can see we are getting 0. That means we don't have duplicated rows in our data frame. Okay. So since we are dealing with machine learning algorithms, these algorithms often take a numeric values as input, but in our data frame or in our data, you can see that we have one column, the class attribute column, which is also our target column. It contains categorical values. So basically, what I'm going to do in the data pre-processing step is that I'm going to be converting those categorical values to numeric values, and I will be using the label encoder. Okay. So data pre-processing. So for this, I'm going to, as I said, I will be using the label encoder. So I'm going to import the model first. So from sklearn dot pre-processing, I'm going to import label encoder. Okay. So when I execute this cell, we will have successfully imported the label encoder. That we are going to use that now to encode the categorical values in the attribute class. So let's start that process. So for that process, I'll first specify the columns to encode. So for this case, we only have one column, that is the column class. So I will create a list. Create a list of the columns to encode. The columns to encode. For this case, we only have one column, so I'll create a variable columns. Then create the list, so it's column class. Then after this, I'm going to create a copy of the original data frame so that when we perform the encoding, we will not be interfering with the other attributes that we won't be interfering with the other attributes. So okay, so we're going to create a copy of the original data frame df. So I'll create a new variable and I will name that encoded df. Then while copying that original data frame to our new data frame, I'm going to use the copy function. So df.copy. Then the next step is all about initializing the label encoder. So I'm going to initialize the label encoder and apply the label encoding. So we initialize the label encoder. So label encoder, label encoders. Then I'll start while encoding. I will be using a loop. So I'll be using a for loop. So call, just a short form for columns in our. So for call in columns, columns is the variable that is storing the list of columns to encode. Then we are going to create a new instance of the label encoder class. And when we do that, we'll be associating that label encoder to the current column. Okay. Then we apply the label encoder to encode the categorical values in that column. Okay. So label encoders. Okay. So label encoders is what we initialized earlier. Okay. Then because we are using the label encoder, this is where we are going to apply that. So label encoder. So this is where we recall our model that will be used to encode the categorical values. So after that, we are going to apply the fit transform method of the label encoder to the specified column, encoded df call. Then we are going to fit and transform. So label encoders call. Then we fit. Then transform. So we are encoding the columns inside this data frame. So we can just paste it inside here. Okay. So after we are done with that, we can then print our output. So encoded df. Then I will just use the head method to see if we were successful with that. So I'm going to execute this. So when I run this code, you can see the class attribute. We have now encoded the categorical values, and by that we just assigned new numeric values for those categorical values. So also remember, earlier on we copied our data frame to the encoded new data frame, and that called encoded df. So what I'm just going to do is I'm going to now copy whatever is in the encoded df back to our original data frame. So you can just say here df. Then instead of the head method, you can just copy, use the copy function. And then after we are done with that, df.head again. When we execute that, you can see we're still obviously getting the same result. But moving forward, df is what will be holding or is the variable or is our data frame. Okay. So now that we have label encoded, or we have converted the categorical values in the class attribute, we can now start the process of building our models. So the algorithms that we are going to be used, so I'll just state them. So these are the algorithms that we are going to be comparing in our analysis, and basically see which algorithm is basically outperforming the rest. So I will start by importing the modules. So for these algorithms, these are the models that we are going to be using. So I've imported the models for the logistic regression, the support vector classifier, the decision tree, stochastic gradient descent, as well as the x-axis. And for other tasks such as the splitting our data into the training and the testing sets, so I've imported the model for that, the train test split. And in our case, we are going to standardize our data. So I've imported the model for that, and that is the standard scaler. So again, I'll also import the evaluation metrics. So the evaluation metrics. I will import the classification report, the accuracy score, also the confusion matrix, and also the precision recall curve and the ROC curve, as well as the area under the curve models. So for the evaluation metrics, this will be the models. Okay, so I'll just run this cell to import these models, and also this cell to import the evaluation metrics. So we have imported all the models, all the modules for this analysis. So we move on to building our model, and I will start with defining our features. So I'm going to define what are our features or the dependent variables, as well as the target variable. So let us define the features. So when we say this, we mean the independent and dependent variables. So let's so X will be our dependent variables, the inputs. So for our case, our dependent variables will be, or our features will be each and every column except the class attribute. Okay, so for that, I'm going to ease in that process. I'm going just to drop the column class from the dependent features. So df dot drop columns class. So I'll be dropping that from our dependent features or variables. And so I can just use a comment here and say defining the dependent variables. Others will say features. Okay. Then after this, defining the target variable. Target variable, I'll say y equals df. Then it will be the column that we dropped. So plus, that will be our target variable. So when I execute this, we will have now defined what is our dependent variable and what is our target variable. Then from here, we move on to splitting data to training and testing set. Now, for splitting, I'm going to specify the variables that will be holding our training as well as the testing data. So as usual, we'll be using the normal xtrain, ytrain. So xtrain, xtrain, xtest, ytrain, ytest. Then for this, we are then going to recall the train test split module. So this will be using this to conduct the splitting process. So then we specify x, y, then specify the test size. In this case, I'm going to be using 0.25. So 25% of our data will be used for testing, while 75% will be used for training our models. And the random states, I'll say use 42. Okay, so this is the how we are splitting our data. After splitting our data, when we look at our data, we can see that we are dealing with data in varying scale. Remember, we imported the module for that. That is the standard scalar. So the first thing, I'm going to initialize the standard scalar. So initialize the standard scalar. I'll just create a variable scalar, then recall the module. So standard scalar. Then we fit the scalar to the training data and transform it. So fit the scalar to training data and transform it. So for this case, I'll create x train scaled. So this is the variable that will be storing our training data. So then scalar.fit, then transform. So we're using the fit transform function in the scalar. We are using the fit transform from scalar. Then what are we transforming? That is the training data. So x train. So after fitting the scalar to our training data, we are going to be using the same scalar, but for this case we are only going to transform the testing data. So transforming the training data. Okay, so for this, again, x test scaled, then scalar, we recall the scalar, but for this case, as I said, we are only going to transform. So transform the x test. Okay, so when we execute this cell, we will have scaled our data. Okay, so after scaling our data, then we can start now building the models. I will start with the logistic regression. So you can say building the models, and then start with the logistic regression. No, logistic regression. This is a classification algorithm. So let's start building our model. So I'll start by creating an instance of the logistic regression. So creating an instance of the logistic regression. So here I'm going to, let's say, LG model. So LG is a short form for the logistic. So logistic model, then we create an instance for that. So logistic regression. Then we are going to specify the max iteration. So max will set a value as 1,000. Then after creating that instance, we are going to fit the model to training data. So LG model dot fit. Again, we are fitting this to our training data. So that's the X train. So X train scaled, Y train. So basically, what we are telling our model is that we are fitting you to our training data so that you learn or discover the relationship between our input features and our target variable. And after you have learned that relationship, we need you now to make predictions. So make predictions on the test set. Making predictions. So for the predictions, we are making the predictions on a testing set. So say Y pred LG. Then you can say, you can recall LG model dot predict. Then we're predicting this using the X test. So X test scaled. Okay. So after we have made our predictions, we can then move on to evaluating our model. So model evaluation. For the model evaluation, I will use the confusion matrix, the classification report, as well as the PR and the ROC curves. So let's start with the confusion matrix. So already I imported the confusion matrix modules. So For the model evaluation, as I said, we start with the confusion matrix. Confusion matrix. So I'll just print confusion matrix, matrix. Then the y-test. These are the actual values, while we are comparing that to the predicted values. So y-pred LG. Okay. So when we execute this, this is the output that we are getting from that. So basically, the confusion matrix, this is a way, or it provides a detailed view of the model's performance. And by this, it is showing how many instances were correctly or incorrectly classified for each class. Or remember, we have two classes in our classification. So this is class 0, while this is class 1. So when we look at the true negatives, 89 represents the count of the true negatives. These are instances where the model correctly predicted the negative class. And remember, for us, the negative class are the patients that the model predicted that whom did not have a heart attack. Okay, so that is the true negatives. And for the true positives, 164 represents the count for the true positive. So this is these are the instances where our model correctly predicted the positive class. So when we talk about the positive class, it means that the model correctly predicted that these patients did have a heart attack. While for the true negatives, for the false positives, 39. So 39 represents the count for the false positives. And when we look, or when we say false positives, these are the instances where our model incorrectly predicted the positive class when the actual class was negative, or it was supposed to be negative. So in other words, our model predicted that these patients did have a heart attack, but in real sense, these patients did not have heart attack. And lastly, we will be talking about, and lastly on our confusion matrix, we are talking about the false negatives. So 38 represents the count for the false negatives. And in this case, these are instances where our model incorrectly predicted a negative class when the actual class was supposed to be positive. So with reference to our in our examples that we are showing here, is that our model predicted that 38 patients did not have heart attacks, but in real sense, these patients did have heart attack. So that is our model evaluation according to the confusion matrix. So this is how our confusion matrix is enabling us to view the model performance in terms of how it is predicting the positive classes as well as the negative classes for our analysis. Okay, so that was all about the confusion matrix. We can also perform another model evaluation technique. And by this, we are going to be using the classification report. Okay, so let's do that. So classification report. So for the classification report, I will just be using the same thing. So for the classification report, I'll just change this to classification report. So classification report. And for our classification report, again, the y-test, this represents the true values, while the y-pred, these are the predicted values according to our our according to the logistic regression model, and we are going to print so that we can see how our model is performing. Okay, so for the classification report, this is the output that we are getting from that, and I will explain some of these metrics that we are getting from this report. So when we talk about precision, what it entails is that precision is the proportion of instances predicted as positive that are actually positive. So by precision, what we are doing is that we are measuring the model's ability to avoid false positives. As we are trying to avoid the false positive by predicting the positive class as accurate as possible. And for the recall, this is also known as the sensitivity of our model. And recall is the proportion of the actual positive instances that were correctly predicted by the model. So by recall, what we essentially mean is that out of the pool from which we are selecting, what is the proportion or what is the actual positive instances that we are trying to predict. And by the recall, it measures the model's ability to capture all positive instances from our sample. And lastly, we have the F1 score. And for the F1 score, this is essentially a harmonic mean or of the precision as well as the recall. And in most cases, it provides a balanced measure that considers both the false positives as well as the false negatives while doing the classification. So I'm going to explain the precision values as well as the recall values from which our model is predicting. And I'm going to explain that with respect to our data set. If a patient is going to have or is showing signs of having a heart attack or not having a heart attack. So those are our classes in this data. So for class 0, essentially, this is the class that indicates that a patient is not having a heart attack. So this is for the class 0. So for our precision, we are getting a value of 0.7 or 70%. So with precision, out of all instances predicted as not having a heart attack, that means the negative class, 70% were indeed negative. And this indicates that the model is predicting about 70%. This indicates that when the model is doing the prediction, it is correct 70% of the times when it's predicting that the person is not likely to have a heart attack. And when we look at the recall, we are getting the same recall of 0.7 or roughly 70%. And by this, we can say that the model correctly identifies 70% of all actual instances where the person did not have a heart attack. Okay, and for the F1 score, again, we are just getting the same value of 70%. And as I had said earlier, this is just the harmonic mean of the precision and recall for the negative class. And for this case, yeah, it's 0.7. Okay. So for the positive class, we are getting a precision of 0.81. And by this, again, out of all instances predicted as having a heart attack, so out of all instances where our model was predicting that the patient is having heart attack, 80% were positive. And this indicates that when the model predicts that a person is likely to have heart attack, it is correct by about 81%. And for the recall, we are also getting a similar value. And the model correctly identified 81% of all actual instances where a person did suffer from heart attack. And when we look at the overall accuracy of our model, we can see that we are accurate at about 0.77, or in other words, when you convert that to percent, we are accurate at about 77% of the times that we are making these predictions. So from the classification report, I think by now you have an understanding of how our model is generally performing. And when dealing with classification analysis, these metrics are important because they explain to you how your model is generally performing. And there are some things I'm going to add on this that will give a clear picture of why we use these reports when doing this when building these classification models. So generally, as you can see from what we have been doing, is that when designing a model, for this case to identify heart disease, the choice between the precision, the recall, as well as the F1 score usually depends on the specific goals as well as the consequences that are associated with either the false positives as well as the false negatives. Okay, so let me redo the confusion matrix because this one is going to be very important in our analysis. Okay, so for our confusion matrix, we identified what are the location, or what are our false positives as well as the false negatives. So for our false positive, we saw that 39, this represents the false positives, and for our false negatives, 38 represents the false negatives as per our data. Okay, so when we talk about false positives and false negatives in terms of our model, a false positive occurs when the model predicts that an individual has a heart attack. That means that is a positive prediction, but in reality the individual does not have a heart attack, so that's a false positive. And when we look at what is the consequence of your model predicting a false positive, so false positive may lead to unnecessary, in our case that is, the false positives may lead to unnecessary medical interventions, treatments for the individuals who do not have heart disease. But when we misdiagnose this patient, we are expecting that they will undergo further medical interventions, and by this case we will be treating a disease that it's not there. So that is the consequence of making a false positive. And when we talk about the false negative, so our false negatives here occurs when the model predicts that an individual does not have heart attack. That means it's a negative prediction, but in reality that individual does have a heart attack. It can be particularly costly, as missing a true positive case, for this case heart attack, may lead to delayed medical interventions, and if this is left unchecked, it might result in serious health consequences. So you might imagine this in a real case scenario where you misdiagnose an individual not having heart attack, but in real sense this person does suffer heart attack, which can be very fatal. And when you are trying to maybe improve your model to make better predictions, these are the two things that we mostly focus on. So if you are building a model, and if the false positives are costly, so when we are trying to build a model and our false positives become costly, so that means if our model is making more of the false positives, okay, Then our focus will be on precision. So basically, if our model is making more of false positives, then our focus will be on precision. So a higher precision ensures that when the model predicts a positive case, it is more likely to be correct. Okay. And if the false negatives are costly, in this case, what we are going to be focusing on will be the recall. As when you focus on the recall, it ensures that that within the pool of tests that we are trying to make these predictions, within that pool, a higher proportion of positive cases are correctly identified. So when we focus on the recall, we are trying to trying to prioritize capturing as many true positive cases as possible. Also, another case might arise if our the consequence of the false positive as well as the false negative are almost the same. Then our focus will be the F1 score, and this provides a balance between the precision and recall. So by that, it is making it suitable when there is an even class distribution. So if you are tackling a case where there is an equal class distribution, then F1 score will come in handy. Or if when the false positive as well as the false negative have a comparable impact or consequence, then when you're trying to improve your model, what you are going to focus more will be the F1 score. So with that in mind, we are going to move forward to see how our model, we're going to move forward and apply what we have previously learned, and we're going to do that to plot the PR, that is the precision recall curves, as well as the receiver operating characteristic curves, to see how our model is performing. So predicting probabilities of the positive class by probes. So I'll just create a new variable and name it y probes. So y probability for our logistic regression, so LG. Then I will recall the model, LG model. Then we are going to use the predict function, so predict, and inside the brackets we are going to, so when predicting, we are using the predict prober function, so predict prober. Then we pass our testing set, so X test scaled, okay. And essentially our values that we're going to generate will be between 0 and 1. Okay. So after making our predictions, we are going to calculate the precision recall curve. So our next section will be calculating the precision recall recall curve. Essentially, the precision recall, we are going to use the precision recall curve function to calculate the precision as well as the recall values for the different probabilities threshold. So earlier on we determined, or we calculated the probabilities. So then we are going to calculate the precision recall curve using the probabilities. So precision recall. So we are going to use the precision recall curve function. So the precision recall curve function. So precision recall curve function, and inside the brackets we are going to pass in the y test, plus our variable that is storing the predictions. So we pass those in as our arguments. So by this we will be calculating the precision recall curve. Remember, we have two curves. We have the precision recall curve as well as the receiver operations curve. So for that, again, we will be using the false positive rate as well as the true positive rates. So those are the calculations that we're going to be making. So again, calculate the ROC curve. So here we will be using the ROC curve function, and it will be used to calculate the false positive rate and the true positive rate at various probability threshold also. So again, FPR, TPR, then so from here we recall the function. So that is the ROC curve. Then from here we pass in our what we will be using to plot this curve. So that will be again the y-test, then the probabilities. I'll just copy that and paste it here. So after we are done with this, so after calculating the precision recall curve as well as the ROC curve, we then calculate the area under the curve for both curves. So we are going to calculate the area under the curve for both curves. Okay, so let's start with the precision recall curve. So I'll create a variable precision recall area under the curve. So this is the variable. So we'll use the awk function. So from here we are plotting precision and recall. So recall precision. So this will calculate the area under the curve for the precision recall curve, and for the ROC curve, again we'll say ROC area under the curve. Again we'll use the awk function, and here it will be the true positive rate against the false positive rate. So FPR T, so it will be true positive rate against the false positive rate for the ROC curve. So after we have calculated those curves, we can then plot those curves. So we'll start with I will start with the precision recall curve. So for the precision recall curve, so the first thing that I've done is creating the figure and defining the figure size. And then, since we are creating two plots, I've used the subplot function. Then we plot the precision against recall curve. Then dark orange represents the color of our line. The line width will be 2. Then provided the X labels, the Y labels, the title, as well as the legend. So I'm going to execute this cell. So when we run this cell, this is the curve that we are getting. This is the PR curve, the precision recall curve that we are getting. And we are getting an area under the curve as 0.91. Okay, so this is for the precision recall curve. We're going to repeat the same, but for this it will be the ROC curve. So maybe we can introduce this here. So this is the precision recall. So for the ROC curve, this is the output that you are getting. So this is the receiver operating characteristic curve, the ROC curve, and from the ROC curve we are getting that that the area under the curve is 0.86. So for the PR curve, the precision recall curve, we are getting that the area under the curve is 0.91. And when we talk about the area under the curve, this is a summary measure that considers the trade-off between the precision and recall for various thresholds. So a higher area under the curve of the precision recall curve, as you can see, we are also getting a higher area under the curve of 0.91. Remember, this figure is between 0 and 1. So a higher area under the curve of the precision recall curve indicates that the model has a strong ability to balance the ability to balance precision as well as the recall across the different classification thresholds. In other ways, it suggests that our model performs well in making the distinctions between the positive as well as the negative instances, especially in scenarios where we might have class imbalance. So in our case, I don't think we have class imbalance in our case. So, but we can see that from the precision recall curve, we are getting a good score out of that, or with respect to the model. And when we look at the ROC curve, we are getting a score of 0.86, and the ROC curve evaluates the trade-off between the true positive rate as well as the false positive rate at the different classification thresholds. And from this, we are getting an area under the curve of 0.86, which again, it's still quite good, indicating that our model has a strong ability to discriminate between the positive as well as the negative instances. And when you have a class distribution that is balanced, that means your classes are none is dominating over the other, then the curve that will give more preference, it will be the receiver operating characteristics, that is the ROC curve. So for our case, we are going to use the ROC curve because our class is, the class distribution is balanced. Remember that in this analysis, we were comparing different classification algorithms, but up to now we have only tackled the logistic regression and seen how we can apply the different evaluation metrics. Now that we have understood how we can apply this the different types of evaluation metrics, so the next thing is that we can now include the other classification algorithms and see how they are performing relative to the logistic regression. And because I have already talked about the different evaluation metrics, so we'll just be plotting them as simultaneously and offering a brief explanation to the metrics that we are getting from this analysis. Okay. So the models that I will be using will include the decision tree classifier. Then I'll also include the stochastic gradient descent classifier, the extra trees classifier. So those are the 4 other classification models that we are going to build. And then after that, we make a comparison with the logistic regression and ultimately select the correct or the model that best fits our data. And by that, we'll be using that now to build the model that will make predictions. Okay. As I said, I will start by importing the modules. So we have imported the decision tree classifier, the stochastic gradient descent classifier, as well as the extra trees classifier. So we will be comparing these 3 against our first model, which is the logistic regression. So I'm going to execute this cell, and by that we will have imported these modules. Then the other modules, such as the classification report, the confusion matrix, these modules we imported them earlier. So before we built our logistic regression, the evaluation metrics, as you can see, we imported them earlier. So I'm not going to re-import those models again. So since we imported the models that for the other algorithms that we will be using in this analysis, so we start by defining the classifier. So I'm going to create. So let's define the classifier. So by this, I'm going to create an object of each regression model, and I'm going to do that using a dictionary. So at first, I'm going to create a variable. I'll name this variable classifiers. So classifiers. Then I'm going to create a dictionary, and in this dictionary, for this dictionary, we are going to create an object for each regression model, for each classification model. So I'll start with the decision trees. So decision trees. Then we create an object for that. So decision tree classifier. Then we create another one. This will be for the stochastic gradient descent. So then lastly, it will be the extra trees. So extra. So after I have created the instances using the dictionary, so the dictionary allows us to create the key and value pair. Then I will use a for loop to iterate over these classifiers. And after we are doing that, we are going to print out the classification report for each and every classifier. So by this, we are going to iterate over the classifiers. And by this, I'm using a for loop. So this is the for loop. Then after that, we are going to fit the model on the training data, as we did with our logistic regression. So we are fitting our X-train data as well as the Y-train. Then after we have fit our model to the training data, we are going to make the predictions. So these are the predictions. And after we have made the predictions, we are going to print the classification report. So we are going to print the classification report for each of our classifiers in this case. So when we print the outputs, essentially this is what we are getting from that. As you can see, we have the classification report for the decision trees. Again, the classification report for the stochastic gradient descent, as well as the classification report of the extra trees. So basically, we are going to be comparing this with the earlier model, that is the logistic regression. So when we look at the decision trees, we are getting a good precision for both classes of 0.98. For the recall, we are also getting good recalls for both classes at 0.96 as well as 0.99. And for the F1 score, again, we are getting a good score of 0.97 for class 0 and 0.98 for class 1. Okay, and the overall accuracy for our case is 0.98. So we can see that decision trees is making good classification. So when we compare this and what we got earlier, we can see that our decision tree model is even predicting, or is more accurate than the earlier logistic regression. So we can put the decision tree as we can rank it as the best algorithm with respect to our analysis. Then we have the stochastic gradient descent, where you can see it's performing quite well as compared to the logistic regression. When you look at the precision, we are 0.72 and 0.82. And for the logistic regression, we got 0.70 and 0.81, accuracy 0.77. So you can see the stochastic gradient descent model is performing better than the logistic regression. When we look at the extra tree classifier, we can rank this as the second best. So you can see again this is performing quite well. When we look at the classification report, it has a good precision, 0.89 for class 0 and 0.90 for class 1. And also for the recall, it's quite high. Okay, so from the look of things, when we do rank these algorithms, we can say that, so we can rank a decision tree as number 1, then extra trees will become the second, gradient descent will become the third, while logistic regression will now become our fourth in terms of making this classification. We can also check in terms of the confusion matrix for each of our models. So let's plot that. Again, as we did earlier, we'll define our classifiers or create an object for each and every classifier that we have here. Then use a for loop that is going to iterate over this classifier, and by this we will be printing the confusion matrix for each of our classifiers. So again, this is the confusion matrix for our classifiers, and for the confusion matrix, basically we are getting we are getting to see how the different models are correctly classifying the different classes in our data. So earlier on, we saw that decision trees was making good, in terms of the classification report. We saw that decision tree was making good classification. Also, when we look at the confusion matrix, we can see that again a decision tree model is performing well, because we can see that we are having less of the false positive as well as the false negatives. And when we look at the extra trees, we can see that it's making less false positive as compared to the stochastic gradient descent. When we look at the false negatives, we can see that again the extra tree model is making less as compared to the stochastic gradient descent. Then also from this, when we do rank these algorithms, you can see again that decision tree is coming out as the best model in making this classification. So lastly, we can also plot the PR curves as well as the ROC curves for these three algorithms, and in some way see if you are going to use the PR curves, if you are going to select these models, which one is performing better with respect to the PR curves as well as the ROC curve. So as we did earlier, we specified the classifiers. So again, if you have other models, you can just be including them here. So we specified the classifier, then we created we instantiated or initialized our models. So those are the decision tree, stochastic gradient descent, as well as the extra trees. Then we moved on to set the subplots. Then we moved on to setting up the subplots. And here, we're using this line to create subplots for each classifier to display both the PR curve as well as the ROC curve, and we're going to do this. We're going to display those curves side by side so that we are able to distinguish for each model. Then, and by this, the number of rows in the subplots or in the grid will be determined by the number of classifiers in the dictionary. So we have 3 classifiers. So that means that we will have 3 rows in our grid, and this grid will be containing the PR as well as the ROC curve for each of our classifiers. Then after this, we are going to iterate over this classifier. So to make our code shorter and to save on time, we are going to use the for loop. So for this loop will iterate over each classifier. And by doing so, we are going to fit the model to the training data. And after we are done with that, we are then going to move on to make predictions on the testing data. So we are fitting the model on the training data. So by this, we are allowing our model to learn the relationship between our input features as well as our target variable. And after making this or drawing those conclusions, we are going to use the same model to make our predictions. And by this, we're just going directly into making the positive, just as we did earlier. We are going to predict the probabilities of the positive class. So by that, this is the line that we are going to be using. We will be using this to predict the probabilities of the positive class. Then after that, we are going to plot the precision recall curve. So we are using the precision recall curve function. Then we plot our chart, and for the chart we'll be plotting that to visualize the area under the curve. So for the area under the curve, it will be the precision against the recall. And this, by using this line, we'll be using this now to plot our actual chart. Also, another plot by this will be the ROC curve. And for the ROC curve, we plot the true positive rate against the false positive rate. So we are using this to plot that at different threshold levels. Then we plot our chart, and this is the code that we will be using. So I'm going to execute this cell, and from this we are going to the outcome from this will be the PR as well as the ROC curves for our 3 classification models. So when I reduce the size for that, so this is the PR curve for the decision tree, and this is the ROC curve for the decision tree. Earlier on, we saw how the decision tree was making a classification. And from the look of things, we saw that the decision tree model was actually better in making these predictions. And when we look at the precision recall curve as well as the ROC curve, we can see that we are getting good scores. For the decision tree, we are getting, for the PR curve, we are getting the area under the curve is 0.99. So it's very close to 1, making it a better model for our case. And when we look at the ROC curve, you can see we are getting that the area under the curve is 0.98. Again, we are getting good score with the decision tree. When we look at the stochastic gradient descent, the PR curve 0.90. And for the stochastic, again for that, when you look at the ROC curve, we are getting the area under the curve is 0.83, which is slightly lower than that of the decision tree. And for the extra tree, we can see that for the ROC curve, we are getting area under the curve of 0.98, which is about 0.03 units less than that of the decision tree. So that's why we were ranking the extra tree as model as the second best model in making these predictions. So this was the part 1. I'm going to do the same for part 2. Again, I'll be using other algorithms such as the random forest and use another type of data set to see how, again, we can apply those algorithms and see how they are performing. Okay, before I sign off, again, if you're new to this place, please consider subscribing to the channel. We are welcoming you to this wonderful community. You can also hit that notification bell, like, comment, and share. And until next time,